Hello everyone. I'm Ron.
Did you use this one?
What do I do?
Okay.
I just okay. I just attached.
That's the mic.
So yeah, that's good. Hi, I'm Roshni. I'm excited to present our work, Bowl, a Deceptively Simple Open World Learner. This is a joint work with my authors, Rupert Mitchell, Subarna Dudi Paul, Kristen Kirsting, and Martin Munch. So most deep learning models are trained and evaluated on clean and curated data set, but the real world is noisy, ever-changing, and often unpredictable. We want models to decide what's out of distribution, what to actively train on, and not forget what was previously learned. This is the essence of open world learning. But how do we achieve these jointly? An open world learner detects when something is out of distribution, so we don't waste resources learning from irrelevant data. It selects most useful examples, those that actually improve the model. Retain knowledge from previous tasks so that the model doesn't forget what it learned before. And these three steps, detect, select, retrain, form the foundation of our method. So our framework BOL unifies these criteria in the prevailing models without any architectural change. It leverages already existing batch norm layer that tracks data statistics to build the three components that function based on the three criteria. This delivers us a lightweight open world learner that consumes less data, requires fewer optimization steps, and works well in unpredictable scenarios. So this slide is a roadmap to what we'll see next. So during training, the batch norm layer tracks the mean and the covariance of the activations layer by layer. We compare the activations of new data to the stored batch norm statistics. We then use these activations to design strategies for OD detection, to actively query useful data, and to retain old data that helps with past knowledge. So to begin with, in an open world, not every sample the model sees is useful for learning. So the first step in BOL is to filter the incoming stream so that it doesn't waste or hurt model performance. Hence, we want the OOD module to reject highly unusual data point, specifically if the data is too corrupted or it's irrelevant for the task at hand. So if the post BN activations for a new input is significantly different, so it's either too high or is too low, then the input is likely an OOD sample. So we exclude the data points whose intermediate activation falls outside the expected range based on the statistics gathered during training. So we formalize our intuition using Bayesian hypotheses between the two modes of activation behavior. Following that, we derive these eta 1 and eta naught score. So for every new input, we compute the Mahalanobis distance between the activations and the BN mean scaled by the inverse covariance. This gives us the eta naught score. However, eta naught only penalizes the large activations. So to fix this, we introduce eta 1, which is an improvement over eta naught that penalizes both large and small activations. So here we can see how BOL distinguishes clean data with the corrupted ones. And we've compared it with predictive entropy, which is commonly used uncertainty measure. So here you can see that predictive entropy has an overlap between the clean CFAR10 and the corrupted CFAR10. So it's really unreliable to use as an OOD filter. Whereas BOL, when using eta 1 statistics, we have a clear separation. CFAR10 has a peak at the lower side, and the corrupted CFAR10 is widespread, and there's a good separation between the two data set. So eta 1 is a good measure for filtering out OOD samples. And after we filter out these samples, this filtered data stream can be large and often partially relevant for the task we care about. So we want to select most informative, unlabeled samples to label and train the model on. So, but not all unlabeled data is worth labeling. Some are redundant and some don't help with generalization. So we designed two heuristics to tackle this based on informativeness and representativeness. We derive both from the model's internal representation via the batch norm layer. For informativeness, we use the batch norm activations. Recall that batch norm standardizes activation based on in-distribution data. So if a new input has widespread activations, it likely represents a novel pattern and possibly valuable to label. Here, sigma square is the variance of post-BN activations. This is high when the input causes unusually high activations and suggesting it might teach the model something new. Next, we compute the cosine similarity between the input and the rest of the pool. So this gives us a high score to the points that are broadly similar to the other inputs in the pool. So we likely get data that we care about. We combine these two heuristics multiplicatively to get our final query score gamma Q. This ensures that we select samples that are both new enough to expand the model's knowledge and relevant enough for its performance. So after querying, it's not just enough to learn this new information. We also need to retain what was learned before. So while continually training on new tasks, forgetting happens when the model overrides old knowledge. So to prevent this, a fixed memory buffer is a common solution, but simply storing data uniformly or at random is inefficient. So inspired by our active learning strategy, we apply a similar scoring to dynamically manage the memory buffer. The score selects samples that are informative, where their activation entropy and the dissimilarity to the other data present in the buffer. So the model is never directly trained on the incoming stream, but it's trained on this curated memory. And more importantly, we train the model on the buffer for just one epoch. So this keeps the learning stable and gradual. At each step, we select a mix of newly queried and previously stored samples and score them using the memory score gamma M. And here, the high scoring samples replace the lower ones, and the memory buffer stays both useful and non-redundant. So now, next we'll see how this takes place in practice. So here, a ResNet 18 model is presented with tasks from split CFAR10 sequentially, and each containing a subset of total classes. The figure is split into 4 panels, T1, T2, T3, T4. The x-axis is the number of batch updates, and the y-axis shows the number of samples queried. So at each active learning step, the model is allowed to query up to 256 samples. And then we mix the newly queried samples with the ones in the memory buffer. And what we plot here is the eventual new number of data samples that the model trains on for the current task. So in the beginning, it starts querying a lot of samples, around 125. And then as training progresses, the number of samples are lower, and it stabilizes eventually. So needing fewer samples when the training progresses. So the purple line here you see is the Bole's accuracy, and the red cross is for GDUM. We compare it with GDUM because both train on just the memory buffer. So if you follow the purple line, it drops slightly when the new task arrives, but recovers quickly, showing that Bole manages forgetting very well. So instead of assuming all data is equally important, Bole actively selects and replaces based on what matters most to preserve. So here's the BOL framework in its algorithmic form. We start with a previously trained model and a stream of new incoming data. We use the eta1 score to identify in-distribution data points and remove irrelevant points. And the remaining candidates form a pool that is indicated by Q. And from there, we apply active query. We use the gamma Q score to pick up most informative samples. And then we update the fixed buffer using the gamma M, replacing less useful samples while retaining the ones that still have higher value. Finally, we train the model only on the memory buffer for one epoch, keeping the compute cost low and while still integrating the new knowledge. So this loops repeats at every new time step, and the model continuously adapts while avoiding forgetting and without wasting capacity on irrelevant data. So now that we have established the BOL framework and its individual components, we will see its usefulness as an open world learner. So in a sense, we will show that BOL requires, in standard continual learning settings, BOL requires fewer optimization steps. In BOL consumes far few data points compared to other methods and gives an effective performance owing to its dynamic memory management. And lastly, we'll show how BOL's cohesive design leads to a suitable, lightweight open world learner. So here we are in the incremental CFAR 10 setting, and here the model must learn, like a ResNet 18 model must learn each new task without forgetting the previous one. So the figure is split into 4 panels again, T1 through T4. In every panel, the x-axis shows the number of optimization steps, and the y-axis shows the test accuracies over all the classes learned so far. So if you follow the blue line for BOL, you'll see that it shoots up to high accuracy almost immediately for every task, whereas the other methods, they climb more slowly and plateau quickly. And what is important that this jump happens every time a new task is introduced. So BOL doesn't require many iterations to recover the accuracy, unlike the replay-based methods or regularization-based methods. So it achieves similar or better accuracy while using substantially fewer optimization steps than other approaches in classic continual learning. This efficiency means we can train the models faster, they can adapt quicker, and still maintain strong performance, which is critical in open world learning scenarios where the model must adapt in real time. Next, in this table, we compare the final test accuracy for the continual learning methods on 2 benchmarks, split CFAR 10 and ImageNet 200. So you'll notice that methods like fine-tune and EWC are at bottom, while replay-based methods like ER and CN perform as well as BOL. BOL is competitive on accuracy while being designed for open world learning. If we reveal the next column, the steps columns, this tells us how many optimization steps each methods need, while many methods or like methods, ER-based, replay-based methods, they match BOL in terms of accuracy. They take an order of magnitudes more steps, meaning much more computation. And this is where our earlier efficiency results come into play. And now we introduce another metric, observed data points. This is where things get interesting. In fixed buffer method like GDump, the ODP or the observed data point stays very low because only a small buffer is ever seen. But in contrast, for methods like ER and CN, it sees all the incoming data for example, for ImageNet, which is huge, up to 1 million points. And BOL sits in between, dynamically deciding what to learn from and what to process, rather than just blindly training on everything or training on too little. So this ODP view is critical in open world learning. It's not just about buffer size, but how much fresh data passes through the system over time. So too many ODPs mean wasted compute, too few ODPs mean one might miss important new information. So BOL strikes like a nice balance. It observes just enough to stay up to date without flooding the learner with all the data. Now we move on to a more real-world setup that simulates open world cases or real deployment cases. So we have our clean images from CFAR10, and which the ResNet 18 model should train and learn from. We have clean images from ImageNet, which also includes irrelevant classes. And then we have corrupted CFAR10, which has various forms of noise and perturbations. So for open learning, we augment the standard continuous learning methods with OD detectors, with active learnings. We do this for fair comparison, because otherwise these methods fail drastically if they are just trained or evaluated on open world setups. So now in the first step, we contaminate the CFAR10 dataset with ImageNet. And here we can see that BOL outperforms all the blue bar here. That's the BOL. It outperforms all the other methods, and the other methods, even if they are patched up with OD detectors or active learning strategies, they don't perform as well as BOL does, and especially like standard continuous learning methods like experience replay, they also fail drastically. And it's like simple pipeline like BOL can definitely beat ad hoc strategies. So in the next one, we add severe corruptions and to the CFAR10 dataset itself. And we can see that BOL is like all other methods, you can see like a drop in the performance as soon as some corruptions are added. And BOL is still resilient, and it outperforms all the methods. So and it doesn't just crumble under adversaries. Now, the last one is where we introduce both corrupted images from corrupted CFAR10 images and clean images from ImageNet. And here as well, we can see that BOL maintains its performance by filtering out what is needed, by making sure that it trains on most useful samples, and at the same time not retaining old knowledge by its dynamic memory management. So here we show that like designing for open world learning, even with just batch norm statistics, we can have like a lightweight open world learner which can outperform like these ad hoc strategies or these standard continuous learning techniques that we have so far. Now, to conclude, I would like to summarize and give a look forward. So BOL provides a monolithic approach towards open world learning. All the methods, all the three components, OD detection, active learning, and continuous learning coordinate via batch norm statistics. And it's a simple plug and play, so it can work seamlessly with any models that already use batch norm layers, which include quite a few models. Third, it's efficient. It uses fewer optimization steps, processes less data, and at the same time gives strong performance in unexpected scenarios. Now, for looking forward, we know that we have better. So BOL uses a diagonal Gaussian approximations for the intermediate activations. So we do have better. There do exist better approximations, but BOL is a nice blueprint for like a principled open world learning. So by anchoring learning mechanisms in latent statistics, we can have better approaches or more principled approaches for open world continuous learning. So this opens up exciting direction for future works. Thank you for listening to my talk. And
so we have one question. So yeah.
In the ResNet batch normalization is already there, right? What is the thing you have done to the batch normalization?
So
Make
in
it better.
SNet, we take the so if the model is already trained on a data set, and then we use the statistics from the batch normalization layer to do OOD and active learning and continual learning. So we just use the mean and the covariance activations. So during inference, we take these activations and then we design these strategies.
So in the OE detection, did you use the hidden layer, the mean and the covariance to?
Yes.
understand?
So here in the so here we calculate X from the all the batch normalization layer, and then the mu bn is again the running mean that is already calculated in the batch normalization layer, and then yeah we have the eta1 formulation using which we decide what point is OD and which point is in distribution.
So this batch normalization you only use for out of distribution detection,
We use it, yes,
and also subsequently.
yes.
Did you compare without using